Hey guys, Miss Miklos here, and today we are going to be using all those identities that you learned about in the previous lecture. And so we're going to start just by reviewing those, and there is a note handout that I would suggest opening up, and that is on the website, so you guys can go ahead and get that. So I want to start with our reciprocal identities, which we should know pretty well. And the first thing that I want to stress to you guys is that if we don't have an angle, you don't have an answer. So it's really important that we are always writing an angle because we know that a trig function does not exist without having an angle. So moving on from that. Sine of theta is 1 over cosecant theta. We've talked about the fact that sine and cosecant are reciprocals. So that means that cosecant theta is like 1 over sine theta. We've also learned that cosine and secant are reciprocals. So cosine of theta is 1 over secant theta, and secant theta is 1 over cosine theta. Our next two that we definitely know, we've learned that tan and cotangent are reciprocals. So tan is like 1 over cotangent theta, and cotangent theta is like 1 over tan theta. And so these 6, you guys should already know. Okay, so having these memorized should not be that stressful. Our final two, though, are kind of new, and we talked about why this works in the video. But tan of theta is also sine over cosine, and cotangent is also cosine over sine. And you guys may have been wondering why we have 2 tangent ratios and 2 cotangent ratios, and you'll see in the different methods that we're using that we tend to actually use these more often, but these are also important, and we'll talk through our thinking on that. The final thing I want to stress is the reciprocal identities also hold when both are raised to the same power. So what I mean by that is tan squared is sine squared over cosine squared. So we can definitely use these when we have exponents. The next 3 only work when we have something squared, and our first one is sine squared plus cosine squared equals 1. And we saw in the last video why this is true, and I want to point out that squared, we always write that in front of the angle, and the reason is we are not squaring the angle, we are squaring the function. When I divide everything by sine squared, I get 1 plus cotangent squared equals cosecant squared. And when we divided everything by cosine squared, we get tan squared plus 1 equals secant squared. So altogether today there are 11 identities that we're going to be using, the 8 reciprocal identities, and then the 3 Pythagorean identities. I would definitely, you guys should already be familiar with these since we took a quiz on them already, but it might be a good idea to write these out somewhere so you have them while we're working on the actual problems today. So now you've been wondering, what the heck are we actually doing with these? And what you'll see in our notes today, we actually are going to look at 2 different types of problems. The first, the directions tell us that we need to write an equivalent expression in simplest form using only sine and cosine functions. So the fun part about this is that there's a lot of thinking going on today, which I personally enjoy. I think it's fun to kind of work like a puzzle and see the pieces that we need to put in place. The other reason why it's kind of fun is because there's more than one way that we can get to the correct answer. And so it definitely shows your personal way of thinking may be different than mine, and we can get to the same place. But what makes these difficult for some people is that there's not a set formula of things to do. And so here's just some guidelines in some things that I always look for. I always look to see if we can use factoring or get a common denominator to add fractions together. Those are just some things that I can see sometimes will help simplify a problem. Another thing that we look for is to see if we can use any of our fundamental identities, especially Pythagorean theorem. So if I see that things are squared, that normally tends to tell me that we might use the Pythagorean identities. Lastly, and this is important to know, if nothing else works, turn everything in terms of sine and cosine. Okay, and often that can be a really efficient way to get to the right answer. Now, that might not always be the quickest way or the easiest way, but it will get us to the right place. So we're going to start here with number 1, and it says sine of alpha cotangent of alpha. First of all, this is a monomial, which makes me happy because that is going to be easier to simplify than if we had 2 terms going on. So the first thing that I would look for is if we could factor anything. Since it's a monomial, we can't. I don't have fractions to add. Then I would look and see, would any of my Pythagorean identities apply here? And they are not going to because these are not squared. So that means that I'm going to try and convert everything in terms of sine and cosine. So I'm going to leave sine alpha as sine alpha. Notice I'm writing my angle. And I know that cotangent of alpha is the same thing as cosine alpha over sine alpha. And at this point, now that I've converted everything in terms of sine and cosine, I can see if anything cancels out. And in fact, these signs cancel each other out. And I am left with simply cosine of alpha. And so what we're seeing here is that our goal is to take an expression and make it more simplified. And the whole purpose in this will be magically revealed to you when you're in calculus, because as we see, we really continue to build on concepts. And in calculus, you will be taking like a big concept and having to do something like this in the midst of that. So that's why we're practicing this now. So by the time you get to calculus, you will be experts and really good at this idea. Okay, let's move on to one that's a little bit more difficult. Number 2, cotangent of alpha times tan alpha plus cotangent alpha. What you guys may notice is that there are actually a few different things that we could do here. Once again, if I really wanted to, I could start by changing all 3 of these into terms of sine and cosine, which I'm not going to do yet. But we could do that and that would work. What I'm going to do here is I'm going to start by distributing cotangent. And the reason why I'm choosing to distribute this rather than like deal with these separately is because of the fact that I foresaw cotangent times tangent. And the reason why this becomes really important is because the product of any 2 reciprocals is always 1. And I foresaw that these 2 are going to be reciprocals of each other, so that makes it much easier for me to work with. So I have 1 plus cotangent squared. Now at this point, there's a few things that we could do. I always look for Pythagorean identities, and looking here, I notice that 1 plus cotangent squared is part of our Pythagorean identities. In fact, 1 plus cotangent squared is equal to cosecant squared. Now, I can see that I've simplified this a lot now because I have a monomial. However, the directions told us our answer needed to be be in terms of sine and or cosine. So I need to think, how can I rewrite cosecant squared in terms of sine or cosine? And it becomes 1 over sine squared, because I know that cosecant and sine are reciprocals of each other. So right now, I'm going to go back and I'm going to show us how we could have done this a slightly different way. So at this point, we have 1 plus cotangent squared. Some of you may have just spaced out on the Pythagorean identities and wanted to go ahead and just use the fact that cotangent squared is equal to cosine squared over sine squared. And if I'm choosing to do this, that's great. We'll still get to the same answer, but it is going to be a little bit more work. Since I'm adding together two things, I know I need to get a common denominator. So I am multiplying by sine squared over sine squared, and I get sine squared plus cosine squared over our denominator, which is sine squared. And sine squared plus cosine squared, it should look familiar to me as well. That is one of my Pythagorean identities, and it's actually equal to 1. So I end up getting 1 over sine squared alpha, which is the same exact answer we got using the different method. Okay, so once again, I only need to use one way, but I want to stress to us that there are multiple things we can do to get to the correct answer. Number 3 is a good one for me to demonstrate in 3 different ways. And once again, we'll see some of them are way faster than others, but I just want, actually no, I'm just going to show you 2 ways. But it would be important just for us to be familiar with these concepts. Okay, for some of you guys, you might look at this and go, oh, I can go ahead and use the Pythagorean identity. And to be quite honest, this is probably how I would think about it. Now, just to back this up a second, the reason why I think we might use Pythagorean identities is because I see this squared term, and the fact that I have it in a binomial should kind of lead me in that direction. Now, this does not exactly match one of the Pythagorean identities like we've seen in our previous problem. However, I can definitely tell that these 2 terms are in sine squared plus cosine squared equals 1. So I need to think, how could I transform this identity to have one of the sides be 1 minus cosine squared? And obviously what I can do, I can subtract cosine squared from both sides, so I get sine squared equals 1 minus cosine squared. So what that means for me is I can take this sine squared and I'm going to replace my binomial of 1 minus cosine squared with just simply sine squared. So I have sine squared theta over tan theta. Now I know I'm not done yet, and so once again, what might pop into my mind when I'm not sure where to go is to turn everything in terms of sine and cosine. So I'm leaving sine squared as sine squared, and I know tangent is like sine over cosine. And when I am dividing by a fraction, that is like multiplying by the reciprocal. So I get sine squared times cosine over sine, and one of the signs in the numerator and the sign in the denominator cancel out, and I am left with sine theta cosine theta. And this is our final answer. We have a monomial, and we have it in terms of sine and cosine. There's nothing more that we could do to simplify this any further. So I think you guys will see this is actually by far the quickest way to do this particular problem. But now I'm going to go ahead and do it in a different way that some of you guys may have started along a different path. Okay, so the other thing that we can do sometimes when I have a monomial in my denominator is that I can split this up and make it 1 divided by tan theta minus cosine squared divided by tan theta. Now this concept of splitting it up only works when we have a monomial in my denominator, because I know this means that both of these terms are being divided by tan. If I had a binomial or something bigger in our denominator, we couldn't do anything with it. So if I'm continuing to work on this, I might think of 1 over tangent as cotangent, for example. And I don't know why I just wrote equals. So if I have cotangent theta minus cosine squared over tan theta. Now, if I'm thinking more about this, I might be kind of stuck here, and I'm going to try and turn everything in terms of sine and cosine. So I know cotangent is like cosine over sine. This would be like cosine squared divided by sine over cosine. So what I'm going to have to do here is make this cosine over sine minus, when I divide, I'm multiplying by the reciprocal, so I get cosine cubed over sine. And what I might notice here is that I can write this as a single fraction, and I also notice that I have a common factor in my numerator. So I can take a cosine out, and I'm left with 1 minus cosine squared over sine. And we actually already kind of looked at this and realized that 1 minus cosine squared is actually equal to sine squared because of our Pythagorean identity. So I get cosine theta sine squared theta over sine. Now when I simplify this, I know sine and that squared can cancel out. And the reason why I can do that in this case is because this is a monomial. I don't have addition. So our final answer would be cosine sine, which is exactly the same as we got using the much shorter way I did earlier. So the whole point here, once again, I want to stress to you that as long as I am using these properties in a correct mathematical fashion, it should lead me to an answer. Now, if I'm coming up with nothing, and we'll see that on some of our problems, then I might need to abandon and try something else. But most of the time, if I continue working down a path, even though it may take longer, it will get us to the right spot. Okay, number 4. Number 4, once again, I have a binomial. So quite honestly, the first thing I would look for is if we have a GCF here, and we don't. So once again, if I don't have a GCF, what I'm going to go ahead and do first is look and see if I can change everything in terms of sine and cosine. So this is going to be cosine squared, and I know that cosecant is like 1 over sine. So I have cosine squared over sine, and I want to somehow get a common denominator. Okay, right now this is like sine over 1, and I can see that my common denominator is going to be sine, so I'm going to multiply by sine over sine. And I end up getting sine squared over sine. So hopefully throughout this you guys are seeing just some little tricks that we can use, and they're all mathematical things that we've learned throughout the year in order to go ahead and simplify. So now that I have a common denominator, I can combine these numerators, and once again this cosine squared plus sine squared should look really familiar to me because I know that that's a Pythagorean identity and it's equal to 1, and my denominator is sine. So this would be our final answer because it's simplified and it is just in terms of sine or cosine. Looking at number 5, we're going back to a problem that's a little bit simpler. We already have a monomial here, so there's not going to be any multiplying or factoring. We don't have fractions at the moment, so I don't need to worry with that. And I also don't have anything squared. So I'm going to try and turn everything in terms of sine and cosine. I know cosecant is 1 over sine theta, and tangent is sine over cosine. And as soon as I do this, I see that some things definitely cancel out. So these sines cancel each other out, and I'm left with 1 over cosine theta, which is our final answer. Number 6 is another one that I'm going to demonstrate in 2 different ways. This looks pretty complex because I have a binomial over a binomial. The one thing that kind of stands out to me though is that I have binomials that have squares, so I'm thinking that it might fit one of our Pythagorean identities. And in fact, I know that 1 plus tan squared is equal to secant squared. So if I wanted to go ahead and isolate secant squared and 1 on the same side, I would subtract 1, and I get tan squared. So I could go ahead and make this tan squared over secant squared. Because I know secant squared minus 1 is equivalent to tan squared, and 1 plus tan squared is equivalent to secant squared. At this point, I'm going to change everything in terms of sine and cosine. So please note that since this is squared, I am making sine and cosine squared as well. And secant squared would be 1 over cosine squared. When I divide by a fraction, it is like multiplying by the reciprocal. And so these cosine squareds cancel out, and sine squared would be my final answer. Now, once again, I think this is probably the easiest way to go about doing it, but I'm going to show you a second method we could use also. Let's say that you only recognize that 1 plus tan squared was a Pythagorean identity. So that would make this secant squared minus 1 over secant squared. I know that I can go ahead and split this up, since I have a monomial in my denominator, as secant squared divided by secant squared minus 1 over secant squared. So I end up getting 1 minus cosine squared. Now looking at that, that looks like one of our Pythagorean identities, and in fact, sine squared plus cosine squared equals 1. So in order to get 1 and cosine squared on the same side, I would need to subtract that, and my answer here would just be sine squared, which is exactly what we got using the other method as well. Number 7, once again, I have a monomial times a binomial, and I'm foreseeing cotangent and tangent multiplying by each other. So I know tan times tan is tan squared. Tan times cotangent becomes 1, because once again, I know when I multiply reciprocals, they end up being 1. And just to show you guys, in case you're confused on that, I know cotangent is like 1 over tan. So tan times 1 over tan, the tans cancel out and we would just be left with 1. Tan squared plus 1, we know is secant squared based on our Pythagorean identity. I know secant squared should not be my answer because the directions tell us it needs to be in sine and or cosine. So I know the reciprocal of secant squared would be 1 over cosine squared. Okay, our final 3 examples are going to hit on our second set of directions, which tells us that our answer should be only a single function or a constant. And what that really means to me is that I shouldn't have any fractions as my answer. So this time, if I'm left with 1 over cosine, I should give secant as the answer. If we look at number 8, I think number 8 is probably the toughest problem we've seen so far. And I notice that I have 2 different fractions. So I'm going to determine what is our LCD. And I know our LCD is going to be 1 plus cosine times 1 minus cosine. So I'm going to have to multiply this first one by 1 minus cosine over 1 minus cosine. And our second one is going to be 1 plus cosine over 1 plus cosine. So I'm going to get 1 minus cosine times sine minus sine times 1 plus cosine over 1 minus cosine, 1 plus cosine. So it definitely looks like we're going to have to do some multiplying here because at the moment these are not like terms. So I'm going to distribute a sine to both terms and I get sine minus cosine sine. And this time I'm going to have to distribute that negative sign, so I get minus sine cosine over 1 minus cosine squared. So if I look in that numerator, I notice that my signs cancel out and that these two terms, even though they look slightly different, are actually like terms. So this becomes minus 2 sine cosine. Just like if I'm adding negative x minus x, I would get negative 2x. That's the same idea here where I'm adding those coefficients together. So 1 minus cosine squared becomes sine squared based on our Pythagorean identity. Now since these are both monomials, I know I can simplify and sine and the squared would cancel out. And I need to think this cannot be my final answer because I should not have a fraction in my final answer. So I need to think, what is cosine over sine equal to? And that is equal to cotangent. So my answer would be negative 2 cotangent x. Number 9 looks similar to some of our previous problems in the fact that I have this monomial times a binomial. The difference this time though, if I am looking for something that is the reciprocal of secant squared, it would have to be cosine squared. Since I don't have that in here, I'm going to do something a little bit different. I'm not going to distribute this time. I'm going to simplify inside here. So I know that cosecant alpha is like 1 over sine alpha. And if I need to get a common denominator, I would need to multiply by sine over sine. So this would make it sine squared over sine times secant squared, and I can actually go ahead and make secant squared 1 over cosine squared. So hopefully we're seeing the better I know these identities, the easier these problems are to work with. When I simplify this, I know 1 minus sine squared is equal to cosine squared based on the Pythagorean identity. So I have cosine squared over sine times 1 over cosine squared. My cosine squareds cancel each other out, and I know that 1 over sine is equal to cosecant alpha. Our final problem of this super long lecture is an easier one because I have monomials, or a monomial I should say. So I'm going to go ahead and just turn everything in terms of sine and cosine. So I know tan squared would be like sine squared over cosine squared. Cosecant squared would be like 1 over sine squared. And cosine is already in terms of sine and cosine, so it's just cosine. And then this is beautiful. Things cancel out, the cosine and the squared. So I'm left with 1 over cosine, which we all know is secant. So I would highly suggest you guys do a lot of these suggested problems just because each one is a little bit different, and I would use these notes as you go through your homework.